and we'll do a quick recap of whatever we have seen until now. Then we'll see why do we need gradient descent as such. Sudipto already says that no, it is used to minimize error, but what kind of error are we looking at and how does minimizing error help us? Okay. And we'll also do some mathematical formulation. I don't want you guys to be those kind of machine learning engineers who just know how to write a few lines of script but don't understand the math behind these concepts. So I want to make sure that we'll derive some equations that we'll be using in our Python scripts as well. And it doesn't have to be, it might look difficult, but it's nothing more difficult than what we have already seen in our engineering schools. We have seen even worse derivations, so this would be a cakewalk. Okay, so there is nothing in over here that you don't already know. I'll try to remind you of those things which you already know from your high school or from your engineering schools, and then we'll take it from there. And then, of course, we want to implement it in Python as well. We just don't want to talk theory in our classes. We'll make sure that we'll implement a gradient descent algorithm from scratch in Python in our Jupyter notebooks. Okay. All right. So this is what we have seen until now. There are two types of machine learning problems that we speak about over here. The first one was the regression problems, and the other one was classification problems. An example of a regression problem could be predicting the price of a stock next year, right? So we are trying to come up with predictions based on the past data. And over here, I'm showing you an example of a linear regression model, which is trying to fit a linear or a line through all these points, right? And another example that I'm giving over here is the movie classification problem. So whether a user will like or dislike a movie, right? So based on the IMDb ratings and the movie time and the past data that was given to us, can we predict whether this new movie, will this user like it or dislike it, right? So based on what we had said, the classification boundary that we have drawn, this point looks like the user is going to dislike it, right? And one thing to note over here about regression problems was that we are always trying to find, or we are trying to predict a continuous valued output, right? So this y-axis would be generally, or the target variable will be generally something like time of the day, the price of a stock, the price of a house, and so on. Whereas for a classification problems, we are trying to answer more of a yes/no problem, or no yes/no answer that we are trying to come up with. We are trying to put things into buckets, saying, is it category 1? Is it category 2? Is it digit 1? Is it digit 2? Is it digit 3? And so on. And that's what we said about classification problems. Until now, what we were doing was kind of fitting this linear regression line using scikit-learn. And scikit-learn was applying some sort of algorithm behind the scenes to fit that line for us. So today what we'll do is try to do that by ourselves and understand under the hood how scikit-learn does it. Okay, sounds interesting to you guys? So over here, predicting continuous valued output, whereas this one is predicting a discrete class or a group. All right, so this is what we have seen about the linear regression problems, given a problem statement that we'll be implementing in our class today as well in the Python script. We'll have on the x-axis, we'll have the number of hours the student studies, and on the y-axis, we'll have the score of a student on that exam. Let's say from the past, we know that these were the scores that were given. The first thing that we as a machine learning engineer want to do is want to fit a line which is closest to all these points. So that could be the simplest model that we could think of. Obviously, this is not the best behavior, right? So this is a simple model that we are trying to create. You could imagine that there could be a model which you could draw which has kind of curvy nature, right? But irrespective of that, there will be also this curve could be represented mathematically as well, right? Just like you could represent a line. So how did we go about representing this line in our computer's memory? What did we say? What parameters do we need to represent this line? Yeah, the m and the b, right? Because the general equation of this line is y is mx plus b, right? And if we have the m, if we know the b, we know how this line looks like. And this is how we could represent this line in our algorithm. So we'll model this using y is mx plus b. And then once we have this line, now making predictions is trivial task, right? Because if for a given x, if you want y, all you have to do is just plug the value of x in this equation. So if you plug the value of x in this equation, you will get the desired or the predicted y in our case, right? So in our case, we are predicting that the score is 60 marks. But let's say that someone tells us that the student actually went to this exam and scored more than 80, 90 marks, right? So this difference between what we predicted and what the actual result was, right? So what the actual result was, now this is the error in our prediction, right? And is our goal to reduce this error, or do we want to minimize or maximize this? Yeah, obviously we want to minimize this, right? Because if this error is less, and if we are doing well for the training examples, at least there is more likelihood that we'll do it during the test phase as well, we'll do much better, right? If during the training itself we are having a lot of error, then doesn't make sense to put that model into practice or to test, right? So that is what we'll try to do. We'll try to see how we can adjust this line to reduce this error, and how can we go systematically, or no, how can we do that systematically about reducing this error as well. So here's a quick quiz for you, just to make sure that you understand these terms. You don't need to know any formulas for these things. Just by looking at the names, you can easily calculate what these quantities are. So if you have a pen and paper next to you, go ahead and calculate the total error, the mean error, and the mean squared errors for this data set. So let's say the predictions that we made was 30 and the actual score was 32, and so on. Can you find what the total error, mean error, and mean squared error for this data set is? Okay, so I've got some answers from Sudipta over there. Nitesh and Himanshu, I think Himanshu just joined in. Himanshu, what we're trying to do is we're going through gradient descent algorithm for machine learning. We just went over a simple explanation or the stuff that we have already covered in the class. So this was a quick quiz that we are trying to do over here. So Nitesh, how are you coming along? Okay, that's fine. No, even if you can just do it in your head, that is good enough. You don't need to have the exact numbers as such. but just try to think how would you go about solving it. So let me just give you a brief context to Himanshu as well, because he just joined in. So Himanshu, what we're trying to do over here is trying to get the error in our linear regression case, right? So we said that we'll model this line over here. We'll represent the model of this world using a simple line. And this line could be written, the general equation of this line is y is mx plus b. If we adjust this m and b, we'll adjust this line as well. So we are trying to see if this was the predicted score and if this is the actual score, what is the error in this case over here, right? So this is the error for this particular point will be the predicted value or the actual value over here. This is the actual minus the predicted, right? So given this data set over here, can we find the total error, mean error, and mean squared error for all these points? If this was the predicted and this is the actual, can we get the total error, mean error, and the mean squared error? You don't have to know the formulas for these things. Just by looking at the name, we should be able to tell how to calculate them. And in the chat over there, just feel free to tell me, no, you could say something like, the way we'll calculate total error will be, no, let's say, for example, 32 minus 30 plus 25 minus 20, 25 plus 20 minus 22, and so on. Okay, so I think here's how you should approach it. All right, so the total error will be just differences over here. So you say the difference over here is of 2, the difference over here is 0, and the difference over here is 2 again and 2 again. So 2 plus 2 plus 2 will give us 6. Okay, so yeah, over here what we are trying to do over here is making sure that you don't always do predicted minus actual or actual minus predicted. You're taking the bigger number over here first, right? So because the way you are looking at it is you're trying to get the absolute values of the difference between these 2 points. Okay, so it's not predicted minus actual or actual minus predicted, it's the absolute difference. The mean error in this case will be the total error divided by the number of observations that we have. So we have 4 observations over here. So 6 by 4 should give us, it would give us 1.5. Is that correct? Someone has given answer as 0.5. So 6 by 4 will give us 3 by 2. So Sudipto and I think Nitesh also did the same thing. The total error was this, and if you take the number of observations, that should give 6 by 4, that should give us 3 by 2, right? What is the average error that we are getting across these 4 points? The average error we are getting is the error over here is 2, 2, 2. So the average error is about 2, 0. If you take average of all these, that will be 1.5. Does that make sense? So it doesn't have to be actual minus predicted or predicted minus actual. We don't care. We just care about the total error. Okay. All right. And the mean squared error should be, whatever this value is. In terms of what you need to do is, for each point, you will get some error. So in this case, the error was 2, right? So you square that thing. For each of these things, you square all of them up and you divide it by the total number of observations. That will give you the mean squared error. Okay, so is this what you guys did? In this case, it won't matter which one you take first, because eventually you are squaring it. So minus 2 square will also give you 4, and 2 square will also give you 4, and so on. So if you say 2 square is 4 plus 0 plus 4 plus 4. This will give you 8, 12 divided by 4. That should give you 3. Is that what you guys got? Okay. So let me know, Nitesh and Sudipto, both of you were doing something else over there. So what did you do over there to get 0.25? Okay, so I'm asking you just because to make sure that I am not wrong over here, because both of you have got getting a different, the same answer. So just making sure that I am not wrong. So please verify it as well, and let me know if we went wrong somewhere. All right, so that should be our no approach in calculating these errors, and our objective for today's class is to find an algorithm that will help us minimize these errors, and specifically we'll be working with a quantity which is mean squared error, which is generally used to quantify the number of errors that we have in our total observations. Okay, so here's our objective. As I said, we have this data set. We want to find a line. That is, finding a line, as I said, is equal to finding the parameters of these lines, right? So some people call it parameter vector as well, right? So let's say you have a line over here. So you have only two things, the slope and the y-intercept, right? As I said, so you have the m and the b. So this m and the b can be for one dimension. If you keep on increasing these dimensions, you will have a plane for, as I said, if you have more than 2 dimensions over here, in 3 dimensions we'll have a plane and a hyperplane and so on. So a lot of people also call this as a parameter vector, because for one dimension we have a line, but if you keep on increasing your dimensions, you will get, this will be theta 0, theta 1, theta 2, theta 3, and so on, right? So if you combine all this theta 0, theta 1 in a vector form, now this is also called a parameter vector. Okay, so just making sure if I by chance I use this name, I tend to avoid using these terminologies, because a lot of these terminologies, when you read it, they might confuse you and you might think, no, what is this person talking about? But it is nothing that we all don't already know. If you instead of calling it m and b, if you think of it as a tuple of two numbers, right? Just if you say this is 0.5 comma 0.3, right? So the slope is 0.5 and the y-intercept is 0.3. Now if you do it for all your dimensions, for one dimension we have just one combination of m and b, but you keep on having it for n number of features that you have, then this vector that you get, this is called the parameter vector. Okay, let me know if that was not clear or I was not able to convey that properly. So we want to find this parameter vector, we want to find this line which will result in the least error. Okay, makes sense, right? We want to find a line that during the training phase itself, it is closest to all these points so that we get the least error. And what could be the solution? How can we go about finding this line? Gradient descent will obviously help us to do that, but how does gradient descent work? Like, what is the basic philosophy behind gradient descent? And to give you some hints on how gradient descent works, so Sudipta has a question over there saying, so the regression line in scikit-learn won't give you the best approximation. So is that a statement, Sudipta? Or so it will try to, any regression algorithm will try to find the best approximation. I'm not sure why do you think that it won't give you the best approximation. So the model that any supervised machine learning algorithm. So Sudipto is saying that when I do sklearn dot fit, and when I say x comma y, right, won't this give me the best approximation, right? Why do I need gradient descent? Well, what I'm trying to tell you, Sudipto, is behind the scenes, this fit method will use gradient descent or some other similar algorithm to to draw this line, to come up with this line. Over here right now, when we were doing scikit-learn, we were just dealing it as a black box. We didn't know how this thing was working. How were we getting this line? But today we'll dive a little bit deeper into it, and that's what I said. No, we'll approach it at a top-down level. First, we saw how to do it with scikit-learn. Now we are doing a little bit. We are digging deeper over here and seeing how this fit method works. Okay. All right. All right, so here's a solution. As I said, gradient descent will help us do that. And to give you an intuition behind how gradient descent algorithm works, the concept is not new. The algorithm is not new. It is well tested and tried over time. So have you guys, I think you must have heard of this story of a spider which tries to climb a wall and keeps on falling again. Can someone tell me what was the moral of that story? So what was the moral of the story of the spider which is trying to climb a cave and then keeps falling? Yep, try till you succeed, right? So trial and error is what, if you want to give gradient descent in another name, that's what it is. Okay, you're just gonna put some random values there. We'll try to see what the error is, and we'll try to reduce it as much as we can until we get a good fit. So we'll start with the random line. Okay, that's what the algorithm, that's the step one of the algorithm. Start with the random values of m and b. Okay, so we'll take any random value of m and b and we'll draw a line, because if you have an m and b, you know what that line looks like, right? So if you have m and b, we know what the m is, we know what the b is, then we can draw a line. And then what we will do is, for this given line, we'll calculate all the errors, right? So we'll calculate the error between this prediction and the actual training point over there, right? So we'll do it for all points over here. This will be for all points. I'm just drawing it for 2 over here because I got a little bit lazy, but this error, you will get it for all points, right? So you'll have error over here, error over here, error over here, right? Do we already know how to calculate the total error or the mean squared error? From if I give you all the errors of individual points, can we get mean squared error? Can we get the mean squared error, right? So we'll calculate the mean squared error, and we already know how did we go about doing it. Yeah, that could be a good starting point, right? So instead of, Sudipto says, instead of just taking a random value of m and b, can we, for b specifically, can we take the min? We know that this line has to be between this range over here. So why not just take the b which is somewhere between the min and the max? Yeah, so that could be a good thing to start off with. Okay, so when we try to implement that today in the Python script, instead of taking a random value, you should find the range and use b somewhere between that range. Okay, and you can also see if that significantly improves your convergence times as well. All right, so given a m and b, we'll calculate the total error. So we'll get the error, and we'll try to adjust this line such that the m and b reduces. So we'll try to adjust m and b such that the error reduces now. Over here, the error was a little bit more, and now we have adjusted the line. You see the line has moved a little bit up over here now. And because of that, this error has reduced. The line which was away from these points over here, this error now is now reduced over here because the line has moved a little bit up, right? So we still have some error, but it is significantly less than what we had before. So we want to adjust M and B such that error reduces. And how do you adjust M and B? Well, and what strategy that we can take that will guarantee that we are actually getting a better line? We'll see that, and we'll try to derive that mathematically as well. But this is the overall strategy. We need to adjust M and B such that the error reduces. Okay, everyone with me until here? So how to adjust? We'll derive it. Okay, we'll see how we can do that, but this is the overall strategy. And we'll repeat this until we find the best approximation. So after a point, we'll see that the error is not reducing a much, or maybe let's say we can have our algorithm such that we'll say for I in range 0 to 10. Now this means that I'm gonna try to do this for 10 times, or 10 times, 0 to 9, right? So we'll try this 10 times, and we'll say, okay, I can't do any more. Whatever I get after 10 iterations, that will be my final line. Okay, so that will be the overall strategy of the gradient descent algorithm. Step 1, take random points, or Sudipto will also try taking B between the range over there. Then we'll find the error, right? Find the error, and third, adjust M comma B so that the error reduces, and then repeat. Okay, so then we'll go again and repeat for n times. So how many number of iterations you want, you can repeat it. After a point, we'll see that we'll get diminishing returns. So number of iterations after that point, we are not getting a better line. So Sudipto, that also depends on how your data set is laid out. Okay, so specifically, whenever you want to think of any thing, always think of outliers. So what happens if there is a data point over here somewhere, right? And let's say if the data set is over here, so does that matter, or no? How will it improve your performance then? So always think of outliers, and that will give you a sense of whether you should do that or not. Okay, all right. So here's a quick question for you, based on whatever you have understood till now about gradient descent. Which of the following statement is true? Gradient descent can be only applied to regression problems. Gradient descent is an optimization algorithm which can be applied to any problem in general. So Sudipto, Himanshu, what do you guys think? Yeah, so it is a general optimization algorithm which can be applied to any problem in general. Right? So it's not necessarily for linear regression. Anytime you find a problem where you're trying to minimize something or maximize something, or you're trying to find the parameters of a few things, right? So AX1 plus BX2 plus CX3, right? So now you want to find the output of this function, you want to maximize it, and you want to find these parameters such that it will give you the best results. So it could be something like you're trying to find let's say the output I'm expecting is the sales of my shop, right? And the sales depend on several factors. Maybe it depends upon how many number of hours I work. Maybe it depends on what kind of products that I have, right? And so on. And you say that, okay, it is, I'll associate some weights to it. And if you want to find how can I maximize this sales, then you can apply gradient descent algorithm to find these parameters which will maximize your sales. Okay, so Sudip, just hold on there. We'll get to that part as well. Okay. All right. So let's go to our Python scripts, and we'll code whatever we have learned until now, and then we'll come back and see the thing that I told you that we still don't know how to do that, about the step 2, right? So in step 2, I'm telling you that adjust M and B. Now just keep this at the back of your mind, that we'll go ahead and code whatever we know until now. But Mihir hasn't told you, or Mihir hasn't told me that how can I adjust M and B such that the error reduces, right? So keep this in back of your mind, and let's code whatever we know until now, and then we'll come over here and we'll again try to see how can we do this. Okay. And to answer your question, Sudipto, just hold on over there. We'll get to that point as well. All right. So let's go to your Jupyter notebooks. Open your notebooks.azure.com, and let's go ahead and write the code for the gradient descent algorithm. Make sure if you are not, if you are signed in, sign out and sign it again so that it doesn't give you any problems. So over here, it signed me automatically, but I don't trust it. That's why I'm going to sign out and sign in again. All right, so I'm just going to go over to my projects. Let's create a new project. So I'm going to call it gradient descent. Let's make it a public project, and let's create. I'm going to create a new Jupyter notebook over here. Again, gradient descent, Python 3.6, and let's create a new one. And let me know once you are ready. So I have also pasted a line of code over there for you to download the data set that we are going to use. So go ahead and copy paste it to your Jupyter notebooks. We have already done this before in our class. So let's come over here. Let's use the curl request, and note that because this is an exclamation mark, our Jupyter notebook is going to treat it as a Linux or a shell command. So go ahead and download the data set. Well, it was pretty quick for me this time. And make sure you have the data set in your folder. So I'm just going to refresh it over here so that we know that we have the student_scores.csv file. It's the same problem that we have solved previously in our class on linear regression. All right, so let's go ahead and do the regular drill. Import pandas. Let's read the CSV file and let's see what's inside it. Okay, so I'm just gonna go ahead and do that. And let me know once you guys are over here. Nitesh, how are you going along? I've got done from Sudipto and Himanshu. Okay. All right, so only new thing that you'd see in this data set over here is last time we did not have this pass column over here, right? So this time I've just added another column over here for pass or fail, right? So 0 means that they have failed that exam and 1 is pass. Tomorrow we'll see how we can do classification problem on the same algorithm as well, or using the similar approach as well. But today we'll just focus on the hours and the scores over here in this data frame. Sure. All right. So can you guys go ahead and plot this out? We have already seen how to do that using matplotlib and in our several of our EDA classes that we did. So go ahead and plot the hours and the scores on a graph and try to visualize it. And let me know in the chat box what kind of plot are you using to visualize your data as well. All right, so Nitish, what we are saying is, can you go ahead and visualize this data? So we have this data set with us, hours and the scores. Can we visualize it using Matplotlib or Pandas data frame, whichever you prefer? Okay, thanks for sending that, Sudipto. Let's just wait over here to make sure that Himanshu and Nitesh are also able to complete that. All right, guys. So this should be pretty straightforward though. So let's see how I would go about doing it. So we know that we need to plot these two things. As I said, now right now let's just focus on the hours and the scores. For the classification task tomorrow, we'll also see the pass feature or the target over here. But let's just see how we can go and plot the hours and the scores together. So pretty straightforward. On the x-axis, I'm going to take the data frame of hours because that is our independent variable. The dependent variable or the target over here is data frame of the scores, right? And once we have these two things, we have already seen how to use matplotlib to do that. So let's go ahead and import matplotlib as well. So I'm going to import matplotlib in my code over here. So I'm going to say import matplotlib dot pyplot as plt. The other thing that I'm going to do over here is also say use a magic over here, which is called as matplotlib. Now this is specific to Jupyter Notebook. This has nothing to do with Python language as such. We are going to say matplotlib notebook. Now this is going to tell your matplotlib or our Jupyter Notebook that I'm trying to use the interactive backend of matplotlib, and that will make sure that our graphs look even better on our notebook. You can do it without this as well, but I'm going to use this magic function over here, which is called as by using a percentile you could do that. So I'm going to say matplotlib notebook. Let's see if this works. Okay, so I've imported my matplotlib. The first time you do that, it might take some time. And once we are over here, we could simply say plot.plot x comma y and then plot.show. Okay, let's just add some titles as well to our graph. We'll see if all right, so we want to make sure that we have got a scribbled line. We want to do a scatter plot rather than doing a line plot. So I'm just going to say dot O over here as well. This will give us dots over here like we have seen this before. Okay. So let's just add some labels to our axes as well. So I'm going to say plot.x label. I have the hours. And on the plot.y label, I have the scores. And plot.title, I can say hours versus scores. Okay, so something that we have already seen this before, nothing new over here. So our job now is to draw a line such that it will be closest to all these points, and we'll be doing it without using scikit-learn. We have already seen how we can do that using the linear regression method, which is available from scikit-learn. But today we'll try to write that same thing using gradient descent algorithm. Okay. So everyone over here, everyone has plotted this, the student hours versus score. We know that this is what the trend looks like. Now all we have to do is try to find a line which will be closest to all these points. Okay, all right, so let's go ahead and write our gradient descent algorithm over here. So I'm going to come over here and I'm going to say define gradient descent. Let me make sure that this is a little bit ahead. All right, so I'm going to write a method gradient descent, which will implement one iteration of gradient descent at a time. Okay, to implement this gradient descent algorithm, I need to give my data set, the input data set that I have over here, right? So I'm going to give my gradient descent algorithm all the x values that I have, all the y values that I have. And in practice, when you do this, you would only do it for your training data set. Okay, right now I'm assuming that this entire thing is my training data. Okay, we have only 25 points over here. Right, so we have already seen this, we explored this data set before. We only have about 25 points. So I'm just going to take the entire thing as my training data. But when you go about actually implementing it, you would first separate it into training and test set, and then only give your training data to it. I'm giving the entire training or the entire data set that I have for the training purpose. Okay, because I'm trying to find a line which is best fitting it. Rather, right now my objective is not to test it on the performance of the model. Okay, I'm trying to find a line which is closest to all these points. So I'm just gonna say I'll take all the x's that I have, I'll take all the y that I have. Okay, the other thing that I'm gonna take is the initial values of m and b. Okay, as I said, the output that we are expecting is a line, right? So we want to get a line, and what are the parameters of this line? The m and the b. If we change m and b, the line changes. So we'll take some initial input or the initial values that we'll initialize our m and b to this gradient descent algorithm. Okay, so these are the parameters that I'm taking inside this function. Next, what I'm going to do is I want to calculate what's the first step. Let's look at the first step over here. The step one is start with the random values m and b. We took that as a parameter input to our function. Now I want to calculate error for all these points. Okay, I want to calculate errors for all these points. The first thing that I'll do is first I'll make a prediction. So here's what the for loop should look like, right? So first thing, I have this x comma y. What I need to do is first also make the prediction on this line over here. We'll make the prediction for this particular point using the random values of m and b, and we'll get some error, and we'll calculate how much error did we get, right? So can you do this first step for me? Can you write it in your code? So what I want you to do is for this one particular point only, start off with just one particular point. We have the data set of entire x comma y in your variables x and y. So this is x, this is y. So we have this entire array or list of values with x and y. So for this particular one data set, can you go through all the x and y's and can you find the predicted values for this particular x comma y? So let me frame it this way. If I was not clear, let me just make sure I go full screen over here. So what I'm telling you to do is, I have this point over here with x comma y. This is again, this is, let's say this is x1, y1, this is x2, y2, this is x3, y3, and so on. For all these points, I have taken some random values of m comma b right now as my input to this function. Can you write the code over there which will make predictions for this, for each of these x comma y pair? So for x1 comma y1, I want you to predict what the output with this random values of m and b is. So you will get a point. This will be prediction 1, prediction 2, and prediction 3. So can you go ahead and do this for me? Prediction 1. This is predict 2. This is prediction 3. Then we'll get some error and we'll do stuff with it. But first, can you go ahead and make the predictions for each x1 comma y1 pair, x2, y2? Does everyone understand the task? Let me know if that is not clear. We are starting off with the random values of m and b that will give input to this method over there. That will be the input to that function. Given that m and b, can you make predictions for each x1 comma y1 pair? Or in fact, you don't even need y1 over here, right? So you don't even need y1 to make predictions. All you need is just x1, x2, x3. Okay, so Deepto, that will work. So guys, if that was not clear, let me just make sure that I explained to you properly that on x-axis is our independent variable hours, and on the y-axis I have the dependent variable or the target that I'm trying to find, which is the score. For each x, I want to predict some score over here. So for x1, I'll make some predictions. So this will be prediction 1. For x2, I want the prediction 2, and so on. So can you find the predictions 1, 2, and so on for each x1, x2 pair, and so on? First of all, when we were doing linear regression, can someone tell me what was the equation that we used to make the predictions? So I had given you a quiz over there with something like this. The line had a slope of 2, and I had said, what is the value of y for x equals to, I said 20, I guess. The equation of this line was y equals to 2x. So you said for x equals to 20, y is 40, right? So what was the equation? What is the general equation did we use to make the predictions? Yeah, y is mx plus b. So that is the equation that we'll use to make our predictions. So our predicted value, this what I'm asking you to do, has an equation of mx plus b. So now is that a little bit more easier for you to understand? That all you have to do is just iterate through all the values of x and get the predicted value as mx plus b. So for x in all x's, you have to do y prediction is mx plus b. All right, guys. So you already know what the equation of that line is, right? And all you have to do is just iterate through all these x's to get the value of y prediction. So let me just go ahead and do that. I think it is pretty much simpler than what you guys might be trying. So here's how you should go about doing it. So all you have to do say is, let's say I'm saying for I in x, all you have to say is y prediction is m times this I, the ith x, right? Or let me just change this notation over here. So I can say all x comma all y, right? So if I can say for x in all x's, y is mx plus b, as simple as that. Okay, is this straightforward? Is everyone with me until over here? Easy? Okay, so instead of just having x over here, I'm also gonna have y predictions or the y actual that we have for each x, because we'll use it in our code ahead. So I'm gonna also take the actual x or the actual y for each x as well. So I'm gonna say x comma y actual, and because I need the y's as well, so I'm gonna zip both of these together. So I want to iterate through all x and all y, and x I'm calling just x, and the actual value of the y for that x I'm calling it y actual. So this is my y predicted, and the actual from the data set is y actual. Okay, so this is the predicted. We already have the y actual over here. So can you go ahead and write the formula for error? What will be my error? What should I write? Error equals to, error at that particular point should be equal to yeah, that particular point, I'm not trying to get the mean squared error or anything else. I'm just saying the normal for that particular point, the absolute error over there, or we don't even care the absolute value. All we care is what is the error. So in that case, the error will be y prediction minus y actual. Okay. And you can try now interchanging them as well, and tell me if you see any effect of if it is actual minus predicted or predicted minus actual. We will derive it as predicted minus actual. So whatever you derive it, based on that you now put the formula over here as well. Okay. So Nitesh, over here it doesn't matter, because ahead in the derivation I will show you that now we'll be using the same prediction minus actual over here. So whatever you use it, whether you use, if you want to use actual minus predicted, predicted minus actual, or no, you want to just do a mod of it, just no, we need to be consistent overall. And there is a reason why we can't do mod over there. So correct me, or let me correct myself. You could either use actual minus predicted or predicted minus actual. All you have to do is just stay consistent with that during your derivations as well. But we can't use a mod over here, because we also want to get the direction on which we want to adjust. So let me come over here. Let's say we are over here and we have this line drawn. Okay. Or let me just have these 2 points over here. So let's say we have this. Oops, I don't want this. Okay. So let's say I just have 2 points over here. Okay. So this is my predicted value and this is my actual value. Okay. And my line is going over here. This is my predicted value and this is the actual value. So do I want my line to go up or down? Should my line move upwards or downwards? Yeah, the line should move down, right? But if during calculating the error itself, I just take a mod, will it be possible for me to know which direction should I move? If I take a mod over here, so whether this is over here or over here, if I take a mod, then I won't know which direction I should adjust my line. And that's why we don't want to take a mod over there. Does that make sense? We want to know which direction the error is, so that we can use that ahead in our code. Does that make sense to you guys, why we are not using a mod over there? You could use predicted minus actual, actual minus predicted, that doesn't matter. But you don't want to take a mod so that you know what direction that error is. Is that clear? Okay. All right. So error, we are saying that no, we'll have prediction minus actual. Now, what is the next step in our algorithm over here? What was the next step? The step 2 says once you have the error, right? So we completed step 1. We have error for each point. So if you print out right now, we'll have the errors for each point. Okay. So once we have the error, the second step is to adjust M and B such that the error reduces. Right now, we don't know how to adjust this M and B, but we know that we have to change something to M and B to reduce the error, right? So let's come over here. Let's say I want to adjust M and B with a small amount. So let's say I'll adjust it as delta M and delta B. Right now, we don't know what the value of this delta M and delta B should be, but we know that we want to adjust the M and B based on the error which is present in our predictions, right? So I'm going to say delta M equals to something, delta B equals to something, and M, I want to say M equals to M plus delta M, and B equals to B plus delta M. Okay. All right. So we don't know the values of delta M and delta B, what this should be. We'll try to figure those things out. but we know that we need to adjust m and b such that the error reduces. So I'm going to adjust m with small quantity delta m and b with delta b. This should be delta b. Okay, and let's now if we know what these two things are, I think we are good to go. Then we just have to just return the values of the m and b that we have found. So we're just going to return m comma b. Let's also return the error in case we want to see how the error is increasing or reducing from our algorithm. Okay, right. So just for the sake of trying it out as well, let's just say delta m is 1 or delta b is 1. Okay, this doesn't matter. I'm just trying to see if this thing even works. Like, are there any syntax errors or not? I'm just putting some values, random values, delta m and delta b, to just see if this method gradient descent is working or not as well. Okay, all right. So let's go ahead and call this method. So how can I call this method over here? So first of all, let me make sure that you have completed this part and you have reached over here. Next, I'm just going to call this method. We don't know what the delta m and delta b should be. Just put some random values over there for us to see if this method even works. So Sudipto says that the error will return only the last value of the error. Yeah, that is true, but that is fine as well. And can you think why? So I'm calculating the error for the overall iteration. Okay, so what we could also say is after you have completed, error is y prediction, y minus y actual. What we could also say is total error, I guess. So what if I do this now? Will this work? Okay, and let's return total error then. All right, so let me just go ahead and call this method as well, and let's see if this even gives us anything, or there are some problems with this. So the method returns m, b, and the total error. So I'm going to say m, b, and the total error is equal to, let's call gradient descent. So I'm going to call the gradient descent function over there. And what does it take in? It takes in all the x's. So all my x's are in the x, all the y's are in the y's, and the m and the b, right? So we have to give some initial values of m and b. And Sudipto was going to try out using the range. What we could also just simply say is just say m is 0 and b is 0. Depending upon the initial values, your algorithm might have different behavior. It might take less time or more time to converge. So I'm just going to start off with m and b as 0. So what we are doing is passing in some random values of m and b, and then after we run the gradient descent algorithm, what we should get is a better value of m and b, right? So this should be better m, better b, right? So because after you have run it, you should get a better values of your better values from your algorithm. So let's see if this method even works. So I'm just going to say, let's just call this, let's just run this and see. First, I'm going to run this cell, and then let's run this cell. So I have some errors over here. Y prediction is not defined. So Y prediction, where am I using? Yeah, so this should be Y pred. Okay, let's try again. I've done several mistakes over there. Okay, so now seems like this is okay. So guys, let me know once you have written the skeleton over here. We don't know what this delta M and delta B should be. That's the suspense of the entire lecture. And that's what we'll try to figure it out in the next couple of slides. But we just started off with some random numbers over here, just saying that, okay, and you can also print it out over here. Let's see what the better M and the B values are. Okay, let's see if I print M and B over here. So for us, we think that the better values of M and B are 25, 25. Okay, we don't know how this happened, or this doesn't even make sense, because delta M and delta B, we're just keeping them, no, just incrementing them. But and you can imagine, because we have 25 points, this delta M, this M is incrementing 25 times, and this B is incrementing 25 times, and that's why we have this 25, 25 over here. Okay, so ideally what we want to do is have delta M and delta B that makes sense. We want to adjust delta M and delta B based on the errors that we are getting, right? That should be the intuition, that we need to adjust the delta M and delta B such that the error reduces. So it should be also dependent on the error itself. So everyone over here, everyone has completed. Okay, so just in the interest of time as well, let me just also give you a helper function over here, which you already know how this thing works. You have already used it as well, but I just don't want you to spend a lot of time writing this function. Let me just go ahead and paste it for you over here. And I want you to add this to your Jupyter notebook. So nothing new, you have already seen. What I'm saying is the way we'll make the predictions for the regression line, or the predicted values over there, is y is mx plus b, right? That's the equation over there. So what I want you to do is just go ahead somewhere on the top over here. Let's just add a cell over here. So I'm just going to add a cell and add this helper method over here, which will be plot regression line. Shouldn't call it plot really. It's just like returning the regression y values over here, right? So all I'm doing is just for x in all x dot values, I'm saying y is mx plus b. That's what you already did in the gradient descent algorithm as well. I'm just returning all the values of regression y to my method over here, right? So let's go ahead and run this as well. And let's call it after we have calculated. I want to plot this on a graph and see how this thing looks like, right? So that's the reason I've given that function to you, plot regression line. So what we should say is the y over here should be plot regression line. Or actually not the y, but let's call it regression line, equal to plot regression line. And then what does this plot regression line take in? X and M and the B, right? So we need the X, the M and the B. Okay, so this will give us the value of regression lines or the line that we want to plot. Okay, and then let's do a plot as well to plot it. So I'm going to plot the regression line for all the values of X, right? So I'm going to say X comma regression line. Okay, and the last thing I want to do is say plot.show as well. And let's see what do we get now. So again, guys, let me know if you don't understand the plot regression line function. We already know what the regression line, the equation of regression line is, right? If you want to draw this line, I'm just saying iterating through all the values of these x's and finding y is mx plus b and appending this to a list so that I get the values of regression y. Does that make sense to you guys? These are our predictions. I'm trying to draw a line on this graph. For each values of x, I want to say y is mx plus b. That is what I'm doing. Does that make sense to you guys? We already done this. Okay, so we got the regression line, it seems. We have drawn a line. We don't know how this fits on the points as well. So what I'm going to try to do is plot these two things on the same chart. So rather than doing it over here, let's just take the same thing. And I don't want to have anything over here. I don't want the plot.show over here. So let's just take this entire thing and plot it over here as well. So I just copied the same thing that we had written above, and instead of having plot.show over here, let's just do a plot.show at the end. Okay, so not a great start it seems. With some random values of delta m and delta b, this is the chart that we are getting, right? With the slope of 25 and 25, this is what we get. So everyone with me over here? Is everything that we have done until now, is that clear? All I've done is just plotted these two things on the same plot rather than having it in two separate plots so that I can see how my line is fitting the points right now. And as you see, we are doing a terrible job because the delta m and delta b, we just chosen some arbitrary values and we haven't thought about it yet. Let me know once you have completed this. And all I've done is just copy pasted the same thing from above. We already wrote the lines of code to plot these points. I just took them from above, put it over here, and just did a plot.show after everything was done. Don't have two plot.shows, otherwise it will give you two different charts. All right. So let's think about how can we go about reducing the error that we are seeing right now. Right now we are seeing a lot of error, and what I said is if we use a correct value of delta m and delta b, we'll be able to reduce the error. And what did I just tell you about what this delta m and delta b? So what we are trying to do is find delta m. Here's our objective. We want to find delta m and delta b such that the error reduces. So intuitively, what you can tell about delta m and delta b, what will it eventually depend on? So you want to adjust m and b such that the error reduces. Now that tells you something about the delta m and delta b equation as well. What will it eventually depend on? So right now this is our error, right? Right now this is our error, and you want to adjust the m and b, or you want to adjust, when I say adjust m and b, that means adjust the line. Okay, now that, though, keep that in mind. Whenever I say adjust m and b, that means adjust the line. Based on what will you adjust the error? Intuitively, what can you say about delta m and delta b? Based on what you should adjust the error, or based on what should you adjust the line? Any ideas? Any thoughts? Not necessarily x and the y, Himanshu. So let me show you. You already know it. You're just getting confused over here. Let's say the line is over here. This is our prediction. This is our actual output. So should I adjust the line? And this is the error. Okay. So Nitesh already has given the answer, but let me just explain Himanshu as well. That Himanshu, if the error is more, will you move the line more? And if the error is less, will you move the line less? So do you agree? So not just y-axis value. Okay, so don't just think in the 2 dimensions over here. That is difficult for us to visualize in more than 2 dimensions. But right now we are dealing with a simple data set, so that's why we have just 2-dimensional graph. But in general, you want to adjust the line in proportional to the error, right? That's the whole idea. You want to adjust the line such that the error reduces. So in turn, this m and b will also depend on error. Is that correct? We don't know what exactly that will be, but intuitively you should know that it will eventually depend on the error that you're getting. Does that make sense? If the error is more, you will adjust more. If the error is less, you'll adjust less. Okay. All right. So what do we know about the error itself? So I said that we'll be using a quantity called mean squared error for our purpose. So mean squared error is the quantity that we'll use. So what is the equation that I said about mean squared error? We could write mean squared error as 1 by n summation of all the estimates minus actual, the whole square, right? So all my estimated values minus actual values, the whole square. And note that these are individual x's. Okay, so this is the individual estimate for that particular point. This is that particular point. At that particular point, you want estimates minus actual, the whole square. That is the mean squared error for the quantity that we are going to look at. Okay, so do we know something about the estimates over here? Do we know the equation for the estimates? So what is estimates equal to? what are the values of estimates of the y predictions? It is mx plus b, right? So this can be written as mx plus b minus, now the actual will be the actual value, the predictions. This is, if this is y axis, this is x axis. The actual value over here will be the ith index of y, right? So there will be y of I. So for that particular point, we'll have mx of I plus b minus y of I. Now this will be the equation for our estimates minus actual. Just keep this in mind. We'll use it going ahead. Just keep it at the back of your mind that estimates minus actual is mxi plus b minus yi. Okay, so let's park it over there, right? So can I also write this mean squared error as just simply saying error square over here? Okay, so I'm saying let estimate minus actual be called as a variable called as error. Okay, and can I just say mean squared error is 1 by n error square? I'm just saying let estimate minus actual be a term called error. Okay. All right, so sometimes what people also do is call this mean squared error, or this the quantity that we are trying to work with, we're trying to reduce. This is also called as the cost function. Okay, so this is also the cost function, because the intuitively the idea is each error is costing you something, right? So this overall equation that you're trying to reduce is the cost function that you're trying to, the function that you're trying to reduce is the cost that you're trying to reduce. Okay, and as I said, there are different notations to it. If you want to just call it in simple terms, you call it mean squared error. A lot of people also mathematically they annotate it, or it's also, you will see that whenever you go through some tutorials, they will also represent it as j of theta. Okay, j of theta, which is in turn dependent on m and b, right? So does everyone agree that this j theta, the cost function, depends upon the m and the b eventually? And that's why I'm writing j theta. And where is this theta coming from? Does everyone remember the parameter vector that I was talking about? At the start of the lecture, I was talking about the parameter vector theta, which was theta 0, theta 1, theta 2, and so on. Okay. Now this might be a little confusing over here, but we'll do this over and over again so many times during this course that you will eventually get a knack of it. So in the back of your mind, you will, theta 0 is in 2 dimensions, this is the b, theta 1 is m. Okay, so it is as good as saying m and b in a vector form. Does that make sense? It is just different notations, guys. It has to nothing, we are not doing math over here. This is notations, this is cryptography. This is just putting it in cryptic form so that it becomes difficult for you to understand. But the reason why I am introducing these notations over here, so that when you go and read something online, you don't think that where is this coming from? What is j theta? Where is j omega coming from? You already know that it is just a different notation. Some people represent this in a vector form, m and b in a vector. Now that will be theta 0, the b will be theta 0, and this is theta 1. So I wrote it in a different way. So b is above, m is over here, this is theta 0, this is theta 1. Does everyone understand when I said theta, what do I mean? And what I'm saying is this j theta, which is eventually a function of m and b, is 1 by n the error square. So can someone tell me what will be the graph of the j theta look like? If I want to plot it on a graph and I have error on the x-axis, what will j theta look like? So let's try to plot it. When error is 0, what is j theta? If error is 0, what will be j theta from this equation? Yeah, 0. So let's plot it 0 over here. If error is increasing on the positive axis, how will j theta increase on the positive axis? Will it increase linearly? Will it increase exponentially? Will it increase at a constant rate? How will it increase? Yeah, it will increase exponentially, right? Okay. And on the negative side, will it also increase exponentially? Because you were doing an error square, so it doesn't matter. So it will look like a parabola. Everyone agree with me on that? Okay. So this is what the graph of j theta should look like. Okay. And what you want to do is now, what we want to do over here is we have started off with the random value of m and b. Okay. So with the random value of m and b, we'll get a random value of error as well. So Sudeep, the -2 square will give you 4. So that is exponentially both sides, right? Doesn't matter. So 1 square is also 1. So if you have error over here and j theta over here, we started off with the random value of m and b. With the random value of m and b, does everyone agree that we'll get a random value of this j theta or a random value of error as well? Okay, so we'll get a random value of error somewhere on the curve. Will be somewhere on the curve over here. Okay, so let's say we are on this curve over here now. Okay, for that particular point, we'll have some x and y associated with that particular point. Okay, or the value of error and j theta associated with that particular point. So now the whole problem boils down to how should we move on this curve so that the error reduces, right? And have we seen this concept before in our engineering schools or in our high school classes? What is the concept that helps us to minimize something? We want to move on this curve such that the error reduces, or we want to, our target is to reach over here. We are somewhere over here. We are some at random point on this curve, somewhere we are there. Now we want to reach to this minima or the bottom of this. Imagine this as a bowl. We are somewhere on the top of that ball and we want to reach to the center over here. What is the concept that can help us do that, find that? Yeah, Sudipto says, no, something with derivatives, right? So we know that derivative has to do something, some role over here. That if we take the derivative over here, now we'll be able to get to the bottom of this curve over here, right? So the whole intuition behind that is, what we could do is, so first of all, also let me also revise one more concept over here. Let's say I have this graph and I have this one line over here. So is the slope of this line positive or is it negative? So let's say if I have a slope of this line, is the slope of this line positive or negative? Yeah, it is positive, right? So anything, so you need to look from this side. If it is rising on on the y-axis, this is a positive slope, right? And if you are looking from this side, it is no, it is diminishing or it is going down on the y-axis, this is a negative slope. Okay. All right. So having said that, let me see if I can erase this now. Okay, so that is good. All right. So over here, if I take a tangent to this point, so if I draw a tangent to this point, okay, now that means I'm trying to find the slope of that line, right? I'm trying to find the slope at that point. If I find a slope at that point, will the slope be positive or negative in this case? If I have a curve like this, and if I draw a tangent over here, right? So the slope of this tangent over here, this is a positive slope, right? So can I say that if the slope is positive, then go in the negative direction of that slope? What you want to do is you want to find out whether you should go up or you should go down on the slope. Can we say that our algorithm should be such that find the derivative at that point, or find the slope of that point at that point, and go in the opposite direction of that slope? Is that a good statement to make? So let me again make sure that you understand. Let's see, actually, now that we have seen this, I can do it over here as well. So mean squared error is estimate minus actual. This is the cost function, mx plus dy, j theta. And I have the nicely drawn curve for u over here, so that it's not so bad. And we need to adjust the m and b. That's what we have already seen. And this is the line which is drawn at that point, or the tangent which is drawn at that point, right? Can we say that if the slope is positive, go towards the negative direction? And if the slope is negative, you want to go towards the positive direction? So over here, the slope is negative. So go towards positive side. Over here, slope is negative. Therefore, go towards positive side. Or sorry, the slope is positive over here, so you want to go towards negative. Is this a good algorithm for us to see which direction should we go on this curve? Does everyone agree that what we could do is to find whether you should go towards the left or the right? What we'll do is try to first find the derivative at that point. We'll find the slope of a line which is tangent at that point. That is the derivative of that point, right? And if we find a derivative at that point with respect to the m and the b, okay? So we need to find the derivative with respect to m and the b, and then go in the opposite direction of whatever that derivative is, okay? So if the derivative we get as a positive slope, then we'll move towards the negative direction. If we get a negative slope, then we'll go towards the positive direction, okay? So in turn, this m plus delta m should be actually m delta m times -1, right? Because if you multiply it by -1, you will go in the opposite direction, or you can simply say m minus delta m as well, okay? But I just did not want to confuse you before saying it. Why is it minus? But the reason why m equals to m minus delta m is because you want to go in the opposite direction of whatever that derivative is. Does that make sense? Okay, all right. So now the only problem that we have to deal with is to find the derivative of the slope at that point with respect to m and b, okay? So let's see how we'll go about doing it. All right, so that's where partial derivatives will come in now. And the reason why we are doing a partial derivative is because we have too many quantities that we are dependent on, right? The error is dependent on m as well as it is dependent on b. Now, if you want to find the value of m, you have to take everything else in this world as constant. So what you have to do is assume that b is constant, and now the only variable in this case should be m. And then you could do a partial derivative of this curve j theta with respect to m. So delta m will be the partial derivative of this curve at this point Now this point is xi comma yi at that point. And is this point constant for that particular error? Right? So the points, the x and the y's are also constant. The only variable in this case should be m, because we want to find how can I change m such that the error reduces. So we already know what the formula for j is. I'm taking the constant out over here. The partial derivative of m, error square. Can you guys go ahead and solve this? Do we know what the formula for error is? I had said that keep that in the back of your mind. Whenever we have error, can we substitute that as mx plus b minus yi? Can we do that? Right. So, and before even you substitute that, we know that d by dx x raised to n is n x raised to n minus 1. So what will be the value of this d by the partial derivative m with respect to error square? So what will be d by dm error square if d by dx x raised to n is n x raised to n minus 1? And right now you don't even have to substitute with respect to error. Now just keep it still, you can keep it on the side. Yeah, all you have to do is just the 2 will come down over here, right? So it will be 2 by n times error. But what chain rule tells us is that if a function f is dependent on g, and in turn g is dependent on x, and if you want to take d by dx of f, that is what we are doing, right? So in our case, the function is the error is dependent on mx plus b, right? So f is dependent on g and g is dependent on x. So error is, we are trying to take a partial derivative of this df by dx. So we are taking a partial derivative of this m over here. So we are doing a d by dm or a partial derivative. Then what chain rule tells us is you can do that. The only thing is you do that derivative, but also multiply that by d by dx of the g. So the g in this case is the mx plus b minus yi, right? And that's what we are doing. We have to still take a partial derivative of with respect to this equation as well. So again, the chain rule says that if f is dependent on g, in our case, the error is dependent on the mx plus b minus yi. So our g is the mx plus b minus yi, right? And we know that this g over here is dependent on the m and the b. So if you want to take d by dx of f or d by dx of the j omega, then you should first take that derivative, that is fine, but also multiply it with d by dx of this intermediate term that you were dependent on. Does that make sense? So the only thing I'm saying is you can't just get away with saying 2 by n times error. You have to say 2 by n times error, but also take a partial derivative of mx plus b minus yi. Can you get the answer for this one? D by dm mx plus b minus yi. Note that in our world, the only variable is m. We are doing a partial derivative with respect to m. Everything else should be constant, right? For we are doing it for that one particular point. For that one particular point, x and the y's are also constant. So can you get the value of this for me? D by dm mx plus b minus y. And guys, don't worry, I'll go over all of this thing quickly again as well, because there is a lot of things to take in, right? uh, but let me know if there was some part that was very confusing for you. I'll stress on that particular part again, but just don't be there and trying to saying that it could be because it was something that you should have already known from your high school. Don't think that. If there is even slightest of thing that was obscure, or something which you felt that no, this is something that okay, this is given, this is how it should be, uh, don't take anything for granted as such. Just tell me that there was something which was confusing. And my question to you right now is, can you take the partial derivative of this thing? And don't even think of just partial derivative, just take a derivative. Just say d by dm mx plus b minus yi. If everything else but m is a constant, if everything else is constant and m is not a constant, what will you get? D by dx mx plus b minus yi. So here's what we will get, right? So we'll be just left with the x over here, because if you take d by dx, oops, that was bad, d by dx of no mx over here, in this case m is the variable. Generally you have x as a variable, so you say d by dx x is 1, but in this case m is the variable, so m will be 1 and x is the constant that will come outside. So d by dx will be left with m, and d by dx, or sorry, d by dm, sorry, that is d by dm over here, this will be 1, right? So x times 1, this will be 1, this is a constant, so this will be 0, and this is a constant as well, so this will be 0 as well. So d by dx of constants will be 0, we'll be left with just 1 over here. So the x will get left out, so 2 by n error times x. So this is what the derivative of that point is 2 by error times x. This is what delta m is. Note that this is something that we were looking for. That was the whole suspense of this class, is how to adjust m and b such that the error reduces. And the answer that calculus has given us is saying 2 by error times x. And as I told you, intuitively you could think that the amount by which you should change the m will eventually depend on error. But an interesting observation that we have got from this result is you should also multiply that by x itself. Okay, that is something that won't come intuitively to us, but when we did the math, you could see that you have to multiply the error times x to adjust the delta m. Okay, so can you also do it for delta b similarly? Do the same thing. You have already done this, just like what you did before. The only difference will be now just take the derivative with respect to b now. Everything else will remain the same, just the last step will change a little. So can you do it for delta b as well? Yep, Sudipto, that is correct. Just make sure that you are answering privately as well, so that I know that how is everyone else coming along. Let me know, guys, if you're getting stuck somewhere. I'll be more than happy to go over a few things again. All right, so everything else remains the same. Again, 1 by n d by d b error square, and this time again you have 2 by n times error. Everything else is same. The only thing is now you're taking a partial derivative with respect to b. Now if you look over here, the m is constant, x is constant, and d by d b will be 1, right? So this will be 1, and this is again 0. So we are just left with 2 times error times 1, right? So the delta b should be 2 by n times error. Okay. All right, so can we go ahead and do this in code now? Now that we know what delta m and delta b should be, if we know what delta m and delta b should be, can you go ahead and do that in our code now? Can you go ahead and do that in the code? You know the equations for delta m and delta b, what should they be? And the only thing that I would ask of you right now is to ignore the 2 by n over here, because that is a constant. Okay. So 2 by n is a constant over here. We'll see why this doesn't matter in a few seconds, but just ignore 2 by n in both of these cases. Ignore the 2 by n. Don't worry about that, because it is a constant and we'll take care of it in next few in one step. We're just left with one more step over here, and I promise that our gradient descent algorithm will be able to find the line that we are looking for. Okay, so ignore the 2 by n. Take everything else from the formula, and can you write that in the equation over here? So what should I write over here? Delta m and delta b. We already derived the equation for delta m and delta b. Ignore the 2 by n over there, because I'll just show you in next few seconds why don't we need it. All right, guys, everyone over here, we already have the equations for delta m and delta b. What I'm telling you is just ignore the 2 by n term over there. So should be pretty straightforward over here. If you look over here, the error for delta m, the equation is, as I said, ignore the 2 by n, because I'll tell you why don't we need that. That's a constant. It is error times x. So all you have to say is just, we have the error over here. So not the total error, but just the error times x, and delta b over here is just the error itself, right? So if you take 2 by n and everything else out, you just left with the error itself, right? So this should be error. Okay. All right. So let's try to run this and see if the equations were correct and if we indeed get the answer. All right. So I'm going to run this cell again and we're going to plot it, try to plot it again now. And we are getting some weird line. What is happening over here? We're getting all our points over here. We're getting a negative line, which is somewhere in the third, fourth quadrant somewhere. And something is going wrong over there. Any intuitions on why that might be happening? Or any idea on why that might be happening? So Sudipta, if you missed out that part over there, we added the equation for delta m and delta b that we just derived, and we tried to see if we are getting the right answers, if the math that we did was right. And it seems like it is still not working. We are getting a weird line like this. Any intuitions on why this might be happening? And again, we need to go back to our whiteboard over here and see why that might be happening. So to give you a hint over here, let's say we have this curve, right? We have this curve over here. Okay. And let's say if I'm too high on this curve, okay, let's say I'm too high on this curve. So what will be the tangent at that point look like? What will be the tangent at that particular point look like? If I'm too high on this curve, will it be almost a straight line? Right? So will it be almost a straight line over there? Does everyone agree on that? That if I am too high on this curve, it will be almost parallel to y-axis. And what is a slope of that line? What will be the slope of a line which is parallel to y-axis or a steep line? What will be the slope? No, it won't be 0. Do the math, right? You already know what the equation for the slope is. Or no, as I had told you when we were doing that the slope, think of it as the amount by which you are rising on y-axis for every one block that you move on x-axis. So if you have a straight line, how many blocks are you rising on y-axis for every unit that you will move on x-axis? Or it might be difficult to think in that terms actually, but the slope of a straight line, if you recall, is infinity. It's infinite, right? So it's a steep slope. The slope is not 0. The slope of a line which is parallel to x-axis, this slope is 0, right? It's a flat line parallel to x. So the slope of a line which is parallel to y-axis is the steep slope. So it's a think of it as a steep slope. And yeah, so you can do tan 90 and all that thing, but just intuitively, it's a steep slope. So it's a very high value, right? That's how you call. Now, if I want to say if the slope is steep, that means it's a straight line. And if it's a steep slope, the slope at that point mathematically it's infinite. Okay. So the slope of this point is infinite. In turn, what I'm saying is delta m is infinite, or delta m will be infinite, because if I take a slope of that point, delta m is the derivative of that point. The derivative at that point will be infinite. And what you're doing over here in your code over here is you are trying to add delta m, and delta m will be, what will be delta m if the error is too high? I just told you the answer. If the slope is too high, the value is infinite, right? So delta m is infinite. So what we are adding an infinite term to it. So what is happening is the technical term is we are overshooting over here, right? We are adding a very large quantity. So in turn, if you want to imagine it on the graph over here, we took a point over here. So this is what is happening on the graph, that we were too high on the line. Let's say if we are too high on that line, the slope was infinite, and we said delta m, adjust delta m so that you increase it and you jumped right somewhere over here, or maybe even over here on the curve, and that just kept on increasing. So instead of jumping that much, that high on the curve, what can we do to jump just a little bit? If we are taking delta m right away, we are jumping too high sometimes. We're taking a big jump. From instead of going from here to here, here to here, we are taking a huge jump from here to here directly. So what can we do to delta m so that we just take a little jump every time? Can I multiply this with a very small number? Let's say if I multiply delta m with 0.001, will I always get a small point over here? Or at least ideally I should get a small point, because even if delta m is too large, if I multiply it by 0.001 or a small number, I'll get small steps. Does everyone agree? If I multiply delta m with a small number, 0.001, example, just an example, will my overall value will be always less? Does everyone agree on that? Okay. So this term that we always multiply that with is also called as the learning rate. Okay. So some people denote it as LR, or learning rate is the amount by which you are learning every time. So you're getting closer to your minima over here. The minima is over here. So every time you're getting closer to your goal. And if you have a learning rate which is too high, you might jump a lot, right? So if the learning rate is too high, you will jump a bigger jump. If the learning rate is too small, what will happen? What will happen if my learning rate is too small? If I'm just doing very small increments every time, if I multiply this with 0.000001, what will happen? Will it take me forever to reach to this point? Does everyone agree? So guys, I got disconnected from my other computer for a while. So just let me know if you have said it already on the chat. I lost the chat window over there. So do you agree that if the learning rate is too small, it will take for us ever to reach the local minima? Right? So we just need to try out a few learning rate values that will give us a good answer. So what you could also think of is with delta m, you're only getting the direction, right? So when we do delta m, we are getting whether we should move this way or we should move this way, right? With delta m, we are getting the direction, and with the learning rate, we'll define how much to move. So this is how much to move, and this is which direction to move. Okay, so that is what we will do. And as you imagine now, if you're multiplying this entire thing with a small number, now does this 2 by n really matter? The 2 by n that we had before, does this now really matter in the equation? Because eventually I'm multiplying that with a very small number. So 2 by n doesn't matter, because even that will be a very small number, right? So 2 by n multiplied with something multiplied with a very small number, that is that entire thing is a constant. So you don't really need 2 by n as such, or even if you add it, it won't make any difference. It won't make much difference over there. Okay, so all you have to do is just multiply this with a small number. So let's say I start off with 0.001. Okay, you can try off with some different values as well. And depending upon your learning rate, you will know eventually. So let's just do it over here actually, 0.001. not this, or it doesn't matter actually. Let's just do it over here. And one thing that we had also said was you have to subtract m minus delta m, because we want to move in the opposite direction of the slope, right? You want to move in the opposite direction of what delta m and delta b should be. So we'll say m minus delta m times 0.001 and b minus delta b minus 0.01. Okay. So the negative over here means that we want to move in the opposite direction of the slope. So that's why I'm adding a negative. All right. So let's run this again and see now if this works. And we got something, right? So this is a much better line that we were expecting. It's still not there. So what is the final thing that we need to do? And trust me, this will be the last step of the class. We are already over time, so sorry for that. But we had a lot of new concepts to cover today. So, and all of that has to be done in one go. It's not possible for us to break it into two classes, because you won't get the sync then. So we are getting a good line over here. Is everyone getting a good line? Reach to this point and get to this line first. Okay, so here's my gradient descent algorithm. I'm just multiplying delta m with a small number, and this is a negative because I want to move in the opposite direction of the tangent. Get to this point and let me know. Okay, so you guys are over here. That's great. All right. So once you are over here, what is the last step you think that we need to do? And the answer lies in the phrase or the story that I started off with. What do we need to do? If the spider has to reach to the top, the only thing left that he needs to do, if we are getting in the right direction, the only thing that needs to do is just keep on doing the same thing over and over again, right? And can we just execute our gradient descent algorithm multiple times so that we get a better fit, better line? Can you just go ahead and do that? Just run this gradient descent algorithm multiple times and see if you are getting it. So all you have to do is just execute this gradient descent algorithm multiple times. So on that curve, if you imagine, we have taken one small step, and it's a good step because so that we know that it's a good step because we're getting a better line now, at least. The only thing that we need to do is just do it over and over few more times. So I'm just going to say for I in range 0 to 10. Now you can select any number of times you want. After a point, you'll see that it you'll get diminishing returns. So I want this, and also let's do a plot. Okay, now let's run this. And we are getting something over here. It seems like the first line was this, the second was this, and we are eventually getting a better line, right? So the last line, the purple or the blue line that you're seeing over there, is a reasonably good line for us to fit on this model, right? Let me know once you have tried this out, and if you have any other questions. That was the objective of our class today, was to find a line that will fit all these points efficiently, or with least errors, and our gradient descent method was able to do that. Let me know if you have any other questions right now. And what you could also do is try to do some animations so that you also see how that line is changing. But right now I'm just plotting it, very simply. But if you want, you can do some animations as well so that the previous line goes away and so on. That will give you a good idea of how that line is changing its parameters. You can also try now plotting the value of the loss over here. I'm not plotting the total error. So you should also try and plot the total error and see how that is reducing as your line is getting better. Okay. All right, guys. So that was it for today's class. I hope you had fun. It was great for me, at least, because there's a lot of math that goes inside it, and it is very intriguing on how the concepts that we have learned in our engineering courses or back in our high school, how can that be applied to solve some interesting problems. Let me know if you have any other questions. And if you want me to go over some of the material that we covered, especially the derivations, I'll be more than happy to do that. I also have a homework for you over here. So if you go to your course page, once you have once you go to your course page, go to the gradient descent class and look at the homework over there. Right, so it's the same data set that we are working on right now, the student underscore scores data set. I want you to write a function which implements a mini batch gradient descent algorithm. Okay, so what's this mini batch gradient descent? The version of gradient descent that we have implemented right now is called as stochastic gradient descent. Okay, the name for the algorithm that we have, or the flavor of gradient descent algorithm that we have implemented right now, is called as stochastic gradient descent. Okay, I hope I have spelled it correctly. So stochastic gradient descent. Okay, and the reason why it is called stochastic gradient descent is that we are iterating through all points one at a time. So this is one at a time. Right, so we are finding delta m's and delta b for each point. Right, what you could also do is, instead of finding for each point, you could collect some points together. So what you could do is collect points 1, 2, 3, and 4 together and do a derivative on that. Then adjust it after doing 1, 2, 3, 4. You could select 5, 6, 7, 8, and then do a derivative of that, and so on. Right, and can someone tell me why will this be more efficient, or why could be this more useful instead of doing one point at a time? Yeah, it's absolutely more faster, right? Because calculating gradients at each point is not that easy, or no, it's compute expensive. So if you do it in batches, then it will be faster, right? So try to do that, implement the mini batch gradient descent. The only difference will be, instead of iterating through each point individually, you will iterate through a group of points, and again you'll have to change the formulas over here. So instead of x, you will have something else. You have a matrix right now, you have one value over there, you have a list over there to multiply that with. Okay, so and the other question is, how does batch size affect the performance of your algorithm? So change the batch size and see how your algorithm works faster or better. Over here also, you could change the learning rate and see how it affects your parameters or your model, right? So if I have, instead of 0.01, let's say if I say 0.05 over here, or let's say 0.005, how does that help? Does that help, or is it worse? So change the learning rate and see what happens now. I made the learning rate small, so seems like it is doing better job. But what if I do, let's say, even smaller? Now, is this better or is it worse? Now I made the learning rate so small that I'm never able to reach to my goal, right? So because the learning rate was so small that it didn't even reach over there. And if I make learning rate too high, let's say if I just say 0.1 over here, let's see what happens. If the learning rate is too high, well, we overshoot in that case, right? We never got to a line which was even better over there, right? So this was one line. Seems like there is one line, the second line, which is closer over there, but we can't even visualize it properly. So it could be there, but we are not able to even see that properly, right? So it is overshooting that in that case. So go ahead and try out different learning rates as well and see how it affects your gradient descent algorithm. If you have any other questions, please do let me know. I am staying back for you to answer any other questions. We had to go significantly over time, so my apologies for that. If you have any other questions, if not, please feel free to drop off. I'll see you tomorrow again. Tomorrow we'll try to do classification task using the same algorithm that we just worked on. Goodbye.